Hi, I'm Mrs. Edwards, and today we're going to go over continuity. Let's go ahead and start with kind of the lazy way of thinking about it. I call it the sloth way. And if you want to know if a function is continuous, it really amounts to, can you draw the function without ever lifting your pencil? Any place that you have to lift your pencil, the function is not continuous. A couple of ways that the function cannot be continuous. One of them is at a hole. Think about drawing a function at a hole. I start drawing, I get to a hole, I have to lift my pencil, go to the other side, and keep on drawing. So functions are not continuous at holes. I'm going to pause there for a second and say, you remember when we were finding out if a function, if its limit existed or not? When we were determining if a limit existed, remember holes were okay. So be careful here to remember that for limits exist at holes, but continuity does not happen at holes. But other places that are similar for both, or that I should say the same for both, is at asymptotes and jumps. If you tried to draw a function and I get to an asymptote, so I start curving up maybe, I have to pick up my pencil, go to the other side of the asymptote, and then start drawing again. So functions are not continuous at asymptotes. Similarly at jumps or breaks, sometimes they're called breaks, if I start drawing and then I have to lift my pencil and then I go to another spot and then I keep on drawing, since I lifted my pencil, the function would not be continuous there. So functions are not continuous at holes, asymptotes, or breaks, sometimes known as jumps. Now a little bit more vocabulary here. Some discontinuities are referred to as removable discontinuities and other ones as non-removable discontinuities. Holes are considered removable discontinuities. And then asymptotes and jumps are considered non-removable discontinuities. When we get to the equations of functions, you'll start to see why this vocabulary has emerged. But for now, let's just remember that holes are removable, asymptotes and breaks non-removable. Then we have a formal definition of continuity. It is a three-part definition. Our other really important formal definition that we've already encountered was whether or not a limit existed at an x value, and that was also a three-part definition. We had the limit as x approaches unnumbered from the right, from the left, and then those two had to be equal to each other. The formal definition of continuity is three parts. Part one is that f of a exists. In other words, I substitute the number into the function and I should get out a real value answer. That's different than limits, because remember, for limits, we didn't care what actually happened at that x equals a value, only what happened as we got really close to it. So here we actually substitute in the number and it has to have an answer. Part two is the limit as x approaches a of f of x exists. So the intended height coming in from the left and right have to go to the same answer. And then the third one is that part one and part two are equal to one another. So f of a is going to equal the limit as x approaches a of f of x. A kind of simplistic way of looking at that is f of a is the actual height of the function at that x value a. And the limit as x approaches a of f of x is the intended height from both. So this is kind of saying the actual height is equal to the intended height from both directions. A really important takeaway that you need to put into your notes and highlight and star, whatever you need to do, is that every single polynomial is continuous for all x values. This is huge because the majority of theorems out there for calculus have a prerequisite that the function that you're working with is continuous. And we can avoid sometimes using this three-part definition of continuity if we just know that the original function we're working with is a polynomial. And then if you're going to use a theorem and you have to say that your function is continuous, instead of going through this whole process and you recognize it's a polynomial, you can simply say, oh, the function I'm working with is continuous because it's a polynomial. Some of you right now are thinking, polynomial? Could you remind me one more time what that is? So polynomials, like if you have a quadratic, that's a polynomial. 2x squared plus 8x minus 7, polynomial. Something that's a line, linear, y equals 2/3 x plus 5. A horizontal line, y equals 7, that's a polynomial. Polynomials take the form of a number x to a power plus a number x to a power plus a number x to a power. The numbers in front of the x, they can be any real numbers, but the exponents have to be positive whole numbers or 0. So we'll look at some examples, but your polynomials are just kind of those basic functions that are smooth. You have cubics, you have 4th degrees, 5th degrees. Okay, so all polynomials, continuous. Let's take a look at these functions here that have been graphed. We want to be able to look at a graph and just quickly determine if it is continuous or not continuous and at what x values that's true for. So without using the formal definition, just quickly for these three, we're looking for holes, not okay for continuity. Not holes, not breaks, not asymptotes. So right here at x equals a, not continuous. X equals a break, not continuous. X equals a, we have a hole, not continuous. Okay, so quickly we can say these are not continuous at x equals a. But if we want to use the formal definition, let's go through part 1, part 2, part 3. As soon as we have found that we have broken one of these parts, we are done proving it, because if just one little piece is not correct, then it's not continuous. All right, let's start with this first graph at x equals a. If we try to substitute f of a, so I plug in a, you go up until you hit the graph, but oh, I'm not hitting the graph. So that means when I substitute a, I don't get out an answer. So f of a does not exist. Therefore, at x equals a, this function is not continuous. Okay, let's move over to the second graph, and we want to use the formal definition to make our decision about the continuity at x equals a. So starting with number 1, f of a exists. Well, if I substitute a in, so I come to a, I go up until I hit the graph, and I look over, and yep, if I plug in a, I'm going to get out the answer 2. So f of a equals 2, so far part 1 has been met. Okay, on to part 2, the limit as x approaches a of f of x exists. Well, coming into a from the left, we're going to a height of 1. Coming in from the right, we're going to a height of 2. So the limit from the left and right are not the same. So that means the limit as x approaches a of f of x does not exist. Therefore, this function is not continuous at x equals a. All right, let's go to the third one and prove using the 3-part definition that it is not continuous at a. Starting with number 1, f of a has to exist. So if I substitute in a, I go up until I hit it, and I hit it right there. So it has an answer of 2. So f of a equals 2. So part 1, check, that looks good, it exists. Then on to part 2, the limit as x approaches a of f of x has to exist. So coming in from the left-hand side as we get closer and closer to x equals a, we're heading to a height of 1. Getting closer and closer to a from the right, we're heading to a height of 1. So since the intended height from the left and right are both heading to 1, the limit as x approaches a of f of x equals 1. So we have satisfied part 2. The limit does exist. It happens to equal 1. But when we get to part 3, the actual height has to equal the intended height. F of A has got to equal the limit as x approaches A of f of x. And since f of A is 2 and the limit as x approaches A of f of x is 1, 2 does not equal 1. So we have broken part 3, and so this function right here is not continuous at A. We're going to look here at one more graph before we move on to the equations. So far, in summary, we know that a function is not continuous at a hole, at an asymptote, and at a break. But it's also not continuous at any spot where the function is not even defined. Here's a graph of y equals the square root of x. Starts at 0, 0, and it's heading over to the right forever. Well, if I try to substitute -1 into y equals square root of x, it's undefined. The graph is not anywhere to be seen to the left of 0. So the function is continuous only over its domain, so for x's that are greater than or equal to 0. So to summarize one more time, a function is not continuous at holes, breaks, or asymptotes, but it's also not continuous any place it's not defined. So in the case of y equals square root of x, anything to the left of 0, the function would not be continuous because it's not defined. All right, now let's look at some equations. We should be able to tell right now from a graph about continuity, but how about an equation? We want to be able to tell if a function is continuous or not continuous, and at what x values is that happening. And then not only do we want to know where the discontinuities happen, but we want to be able to classify the discontinuities as removable or non-removable. All right, so to start with, big picture, I'm going to say this slowly because you got to write this down. Any number that makes the denominator equal to 0, the function is not continuous. Okay, so in this particular case, looking at x plus 2 in the denominator, the number that makes x plus 2 equal 0 is -2. So at x equals -2, we have a discontinuity. The question now is, what kind of discontinuity do we have? Remember, we have removable and non-removable. So let's factor the numerator. X squared minus 4 is x plus 2 times x minus 2. And notice when we factor that, we can cancel the x plus 2's. Cancel. Remove the x plus 2's. When something cancels, it is a removable discontinuity. And remember, removable discontinuities in the graphs, I said those are holes. That's because at x equals -2, the graph of g of x has a hole at x equals -2. Here's my picture of g of x, which is really just like the line y equals x minus 2. The only difference is we have a hole in the line at x equals -2. So when something cancels, it creates a hole, and that is a removable discontinuity. Let's take a look at another one. Okay, so one more time, any number that makes the denominator equal 0 causes a discontinuity. So x minus 3 is in my denominator, and the number that makes x minus 3 equal to 0 is the number 3. So we are going to have a discontinuity at 3. The question is now, is it removable or non-removable? Well, x minus 3 does not cancel with anything in the numerator, so it is not going to be removable. If it's not removable, well, then it's an asymptote. We're going to have a vertical asymptote at x equals 3. So the type of discontinuity that we have is going to be a non-removable discontinuity. Here's another one, just to make sure you've got this down. Any number that makes the denominator 0 is going to be a discontinuity. I go ahead and factor the numerator and the denominator to help me decide what numbers make the denominator equal 0. So I set the entire denominator equal to 0 and solve. Set each piece equal to 0, subtract 3 from both sides to solve the 1 on the left, and subtract 1 from both sides to solve the little equation on the right. And I find out that the two numbers that make the original denominator equal to 0 are -3 and -1. So here are the x values where we have discontinuities. So now the question is, what kind of discontinuity is the x equals -3 and the x equals -1? Well, notice here, the x plus 3 does not cancel with anything in the numerator. We can't remove the x plus 3. So it's going to be a non-removable discontinuity. And that also means that we're going to have a vertical asymptote at -3. When a number makes the denominator 0 but doesn't cancel with something in the numerator, you have a vertical asymptote. So non-removable. Now x plus 1 cancels with x plus 1. We can cancel, remove the discontinuity. So at x equals -1, we're going to have a removable discontinuity. And the look on the graph, when that happens, you have a hole at x equals -1. This happens to have a horizontal asymptote. Here, the degree of the numerator and denominator are the same, and there's a horizontal asymptote at a fraction of the leading coefficients, which would just be y equals 1. So I'm going to have a horizontal asymptote, those little half moons kind of curve in there. Okay, so but notice here at x equals -1 on the curve, if I go at -1 until I hit the curve right there, I have a hole. So removable discontinuity. Last example about continuity. When you see an absolute value in an equation, it's important that you recognize that absolute values are really piecewise functions in disguise. And piecewise functions, those are the ones that cause breaks. You cannot cancel x plus 3 with x plus 3. You can't cancel an absolute value with a non-absolute value. But going back to any number that makes the denominator 0 is a discontinuity. So we know that at x equals -3 that we have a discontinuity. The question now is, what kind of discontinuity do we have? It's a common mistake to say removable discontinuity and accidentally think that we can cancel there. But let's go ahead and look at the graph of f of x. You're probably not super familiar with functions that have a lot of absolute values in them, but as soon as you see a few, you start to get the hang of them pretty quickly. If you're in doubt, substitute a couple of numbers in your head into this function to just kind of understand why there's a break. Let's just throw in a couple of numbers to the right of -3. If I substitute -2 into this f of x, -2 plus 3 is 1. -2 plus 3 in the denominator is 1. Absolute value of 1 is 1. 1 divided by 1 is 1. So we have -2, 1, and we would plot our point. If I substitute, let's say 0. 0 plus 3 is 3. 0 plus 3 is 3. 3 divided by the absolute value of 3 is 1 again. So notice every time I substitute a number to the right of -3, I keep getting out an answer of 1. Now, when you substitute the number -3, we get 0 over 0, which is an error message that does not exist. That's why we have a hole in both of these. Okay, but as soon as I start substituting numbers to the left of -3, let's do, say, -4. -4 plus 3 is -1. Negative 4 plus 3 is negative 1, but the absolute value is positive 1. So we have negative 1 divided by positive 1, which is negative 1. That's why we plot the point down here. No matter what number I substitute in to the left of negative 3, the answer to this is negative 1. So that's why we have a break at negative 3. And so a break is called a non-removable discontinuity because we have a break, a jump. And so we have identified the discontinuity here and classified it.